we're going to use slicing to derive the formula for the volume of a sphere. So pretend this is a sphere. Pretend it's three-dimensional, even though we see that it's only two. And what we're going to do is we're going to do this via slicing. So the first thing I'm going to need to do is I'm just going to take a slice. All right, and I'm taking that slice so small so that right there and there I can assume are straight. Now I'm going to call that infinitely small height delta h. And what I would normally do is I'd have a bunch of horizontal slices going all the way up this sphere. You can do vertical too, I just decided to do horizontal. And what we need is the volume of what we call that ith slice. Because once we have that, we'll use a definite integral to add up the volume of all the slices. So this is the big key. Well, let's see, if we put a point here, if we think about what this slice is going to look like. Imagine cutting this slice out and pulling it out of the sphere, and it would look like a cylinder, a very flat cylinder, with a height of delta h. So maybe we put a radius in there and we'll call it r sub I for right now. So r sub I is that distance right there. Alright, that means we can now do the volume for the ith slice in terms of what we have on here, because the volume of a cylinder is pi r sub I squared and then times the height. And this is all well and good, it's the volume of the ith slice, but right now we've got two variables going on. We got r and we got h. We'd like this to all be in terms of one variable. Well, now there's different ways we could measure h, but maybe I make h to be this measurement here from the center up to my slice. So as you can see, h could also go negative as well, and that's fine. We'll see how that gets handled in this problem. So the goal now is to get a relationship between h sub I and r sub I. Well, if I drop in another radius length here, notice what I have. I have a right triangle that has legs of h sub I and r sub I and a hypotenuse of capital R. And that's going to be my key right there, is that r squared equals h sub I squared plus r sub I squared. I want to sub out r sub I, put in h sub I, so I'm going to solve this for r sub I. And actually, I can solve it for r sub I squared. Save myself a step, is r squared minus h sub I squared. If you take the square root of it, you'll just end up squaring it here. You'll end up back here, and that's fine. There's nothing wrong with that. So pi times r squared minus h sub I squared delta h. Now if we set up our Riemann sum, the volume is approximately the summation from I equals 0 or 1 if you wanted to use it to n of pi times r squared minus h sub I squared delta h. We're going to take the limit as n goes to infinity of this to get it exact. So that will turn it into a definite integral. Pi times r squared minus h squared dh. My h sub I went into an h because I went from the discrete case to the continuous case. Now we're continuously going to add in every possible h value. Now, the range on h, it can go down here and all the way up to here. So if we think about what that is, down here, h would have a value of negative r. Up here, h would have a value of r. So we're going from negative r to r. So there's the integral we need to solve. I'm going to skip that here and come down here. So pi. Now here's something to remember. R is not a variable, it's a constant, it's given. And I'm integrating with respect to h, so that again makes it a constant. So that's just going to be r squared times h. Minus, now h is a variable, so this will be h cubed over 3. So hopefully you see the difference there. From negative r to r. Now some people might like to use symmetry here and just go from 0 to r and then double the answer. That's fine as well. But let's just go ahead and do it this way, just so we see how it plays out. So I'm going to come back here, give myself a little bit more room. And I've got pi times, probably should have this in parentheses there, r squared times r minus r cubed over 3 minus r squared times negative r minus negative r cubed over 3. And last little bit of work is going to be to simplify this. Missing a set of parentheses there. So we have pi, and in the brackets we have an r cubed minus r cubed over 3. Now this will be a negative r cubed, but when we distribute that minus to it, it'll go to positive, so plus r cubed. Now here, we're going to have a negative r cubed over 3 because it's an odd exponent. This will make it positive. That will make it back to negative. So minus r cubed over 3. So we have pi. We can see that we have 2r cubed minus 2/3 r cubed. So we are almost there. If we want, we can go ahead and find a common denominator if you want to see how this is going to turn. If you want to see that step, but you might already see it. This is going to be 6r cubed over 3 minus 2r cubed over 3, which is going to leave us with a 4r cubed over 3, and there's the pi from in front. And we get 4/3 pi r cubed. So we just derived the formula for the volume of a sphere using slicing.